Okay, let's dive into this. We're going to pull back the curtain on something we all use literally every second of the day, but almost never actually see. I'm talking about the invisible world of data transmission. It's a journey that happens in the blink of an eye. And trust me, once you understand how it all works, you'll never look at the internet the same way again.
I mean, really think about it for a sec. You tap send on a photo, and your friend on the complete other side of the planet has it just moments later. How does that actually happen? It's not magic, not at all. It's a brilliant, high-speed delivery system. So let's follow that photo and uncover the secrets of its incredible journey. All right, so the very first thing that happens on our photo's journey is solving a massive problem: size. You see, sending a big file across the internet all in one go would be like trying to shove an entire building through a tiny letterbox. It's just not going to work, right? The system needs a much smarter way to handle it. And that smarter way is to basically shatter your file into thousands of tiny, manageable pieces called packets. Here's a great way to think about it. Instead of trying to ship a whole heavy book, what if you just ripped out every single page, put each page in its own little envelope, and mailed them one by one? That is exactly what your phone or computer does with your photo. And every single one of these little packets is like its own miniature, self-contained parcel. It's got three key parts. First, you've got the header. That's the address label. It says exactly where it came from and where it's going. Then you have the payload, which is the good stuff, the actual little slice of your photo. And finally, there's the trailer. This has a little error check to make sure the data is okay, and it basically signals, hey, this packet is done. Every part is absolutely crucial for the journey. Okay, so now we have thousands of these little packets, all ready to go. But the internet is a ridiculously chaotic superhighway. You've got millions, maybe billions of other packets from other people flying around at the same time. So how on earth do our packets find their way through all that chaos without getting hopelessly lost? Well, the answer is this beautiful system called packet switching. Now, this isn't like a train that's stuck on a single track. Instead, every single packet is its own independent traveler. The network decides the best path for each individual packet at the very moment it's sent. This is what makes the whole internet so incredibly resilient and efficient. If one road is blocked or has a traffic jam, the packets just take a different route. No big deal.
And the hero of this whole process is the router. The best way to think of a router is like a traffic cop standing at an insanely busy intersection on the internet. As each packet zooms up, the router instantly reads its header, that address label, and points it down the best path for the next leg of its trip. This is happening millions of times a second for countless packets. It's pretty amazing.
So, how does all this data talk? In the early days, a lot of data transmission was what we call simplex, which is basically a one-way street, kind of like a radio station just broadcasting out to you. But today, our internet connections are full duplex. This is a two-way highway. It means your device can be sending packets out, like uploading that photo, at the exact same time it's receiving packets, like loading a web page. This is why you can multitask so seamlessly online.
So our packets are zipping across the globe, each one finding its own clever path. But that journey can be pretty rough. Along the way, data can get jumbled up or corrupted by anything from network congestion to just random electronic noise. So that brings up a new problem. How do we guarantee that the photo that arrives is 100% identical to the one that was sent?
Right. What happens if one of those little envelopes, one of those book pages we mailed, shows up all torn and unreadable? Or what if an envelope just gets lost in the mail completely? If even one single packet is missing or messed up, the final photo is going to be a disaster. The system has to have a way to proofread itself.
And thankfully, it totally does. The system uses these automatic error-checking methods. You can think of them as these super diligent digital proofreaders. And here's the clever part. Before sending, your computer does some really quick math on the data inside a packet and gets a unique result. When that packet arrives, the receiving computer does the exact same math. If the answers don't match up, it knows that packet got corrupted somewhere along its journey.
Now, these methods have technical names like parity checks and checksums. A checksum, for example, is kind of like adding up all the numbers in the data to create a single magic number. If the receiver's calculation doesn't create the exact same magic number, it knows something's wrong.
And when that happens, a system called an automatic repeat request, or ARQ, kicks in. It's simple. It just tells the sender, hey, packet number 582 was messed up, can you send it again? A fresh, clean copy is sent, and that ensures the final file is absolutely perfect.
Okay, so we've broken our data down, we've routed it across the world, and we've checked it for errors. But there is one last, and I mean critical, challenge. This digital highway we've been talking about, it's a public space. So how do we protect our private photos, our bank details, our messages from being intercepted and read by someone else?
The answer, and it's a big one, is encryption. Before any of those packets leave your device, they get scrambled into a secret code. It's like putting them inside a digital lockbox. So now, even if somebody manages to grab a packet on its journey, all they're going to see is meaningless, random gibberish. This is the technology that underpins basically all online security.
And encryption comes in two main flavors. You've got symmetric, which is kind of like having one key to a house that you and a friend share. It works great, it's fast, but you have to figure out a secure way to give them that key in the first place. Then you have asymmetric, which is even more clever. Think of it like a mailbox with a public slot on the front. Anyone can drop a message in, but only you have the private, secret key to open the box and actually read what's inside. This is what makes secure communication with strangers, like an online store, even possible.
So just stop and think about what we've just walked through. In less than a second, your photo was shattered into pieces, each piece was addressed, routed independently across the entire globe, proofread for any errors, and kept completely secret inside a digital lockbox, and then a perfect, secure copy was put back together on the other side of the planet. It is an invisible, high-speed ballet that happens every single time you click send. This incredible system was perfected over decades, but you know technology. It never ever stands still. As our world demands even faster speeds and security that's strong enough to resist things like quantum computers, you just have to wonder, what new, brilliant system will power the next generation of our data's journey? And what new possibilities is that going to unlock for all of us?